Yeah, good. Then welcome everyone to the second Func Prog Sweden. We tried to host this second one in March somewhere, but then the coronavirus hit us all, so now we're trying to do it online instead. Yeah, so I'll just kick off a few slides and then I'll hand over to Kiko that's going to do the main speech at this meetup. Let's see. So agenda, a short intro, that's me. Presentation 1, then developing a Monadic type checker for an object-oriented language by Kiko. That's today's agenda. As we're doing this online, we're trying to do it with one speaker and see how it works and the timing. So we try to do it at this time now at 3 o'clock. We'll see how it works moving forward. And also, we're looking to do it again somewhere in June, dependent on interest and if we can find speakers and etc. So this community, we set it up. I think I started the community, me, Matthias, and Tim started the community back in November last year. We had the first go in, I don't remember if it was January. We set up the community because we love functional programming. We try to be open and inclusive. We like to share. And let's have fun and spread functional programming even more. Venue or Zoom sponsor, it's Adabeat, the company I work for. Yeah. And speakers and sponsors, if you want to share or present at the meetup or have a venue. Right now, we're not. I mean, sooner or later, we're going to get out of the Corona stuff, and then we're going to start looking for venues again and try to meet face-to-face instead. But if you have anything you want to present, just contact me or the other organizers, Tin or Matthias, and we'll get you a spot here to present. Yes, and also if you have questions during the presentation, please use the chat. I guess that's the easiest, and then Kiko can see it in the chat, and then he can answer the questions while he's presenting. Yes, that's it for me. I'm going to stop share and now hand over to Kiko. Welcome up on the stage, Kiko.
Ooh. Ooh. Let me see.
Yeah.
Yep. I want to share. Do you see my screen?
Yes.
Yes. Perfect. Let me see if I can make this. Do you still see my screen?
Yes.
Perfect. I'm trying to see if I can have the Zoom so that I can let participants in, but it seems to be a bit difficult. So yeah, we'll see how it goes.
Yeah.
All right. So I'm going to present I'm going to present how to develop a monadic type checker for an object-oriented language. And this is something that we produced as a paper and was accepted at the Software Language Engineering conference. This kind of type checking design or type checking monadic design is not quite my idea. It's an effort by all of these people in here, heavily influenced by Elias Castellgren, who is the person in the first picture, and quite also by Stefan Brandauer. And then at the complete right, we have Albert, and then below we have Tobias and Dave. And all of us kind of contributed, but as I said, kind of the main effort was done by Elias Castellgren, who is now a postdoc at KTH. So I will start with a bit of background information, and then we will see how to create this kind of monadic type checker design. So we use Haskell to build the type checker for an object-oriented language. And this was a research language that uses capabilities, so basically annotations right next to the types. And we've been kind of hacking on this compiler for 4 years, and it's been really great. The compiler is around 15,000 lines of Haskell, and 7,000 lines are really the type checker. Now, of course, in this presentation, I'm not going to go through 7,000 lines of type checker, because as I said, the type checker in this case is for the research language called Encore, and it uses capabilities. And what I'm going to show here is how to use a subset of what we did so that you can get the main benefits, which is basically the monadic design. The talk is going to be about how to write a type checker in Haskell. So I assume that you are familiar at least with reading Haskell, maybe not advanced features, but reading. And this is the tutorial that we would have liked to read before we started doing this kind of type checker. It's targeting researchers and engineers who want to use it in a functional setting, but specifically, as I said, in Haskell. I also provided the link in the meetup, such that there's a paper that feels like a tutorial and that explains basically how to do this. We also provided an artifact. So that means that we provided the code such that you can try it at home as well. The type checker uses the following design. So it's going to use some kind of global environment. It's going to have also backtraces. Now, backtraces are basically information about the context so that whenever you generate an error, you produce an error that is understandable. We're going to show also how to throw multiple, or in the paper, we show how to throw multiple errors using the exception monad. And we show as well in the paper how to do this in two different ways. We will also add to the type checker how to throw warnings. And this is, I think, the coolest thing that I've seen, which is how to prevent statically the use of unannotated abstract syntax trees when one expects them to be annotated. So how can we prevent accessing some kind of abstract syntax tree that is supposed to have some kind of typing information, but it doesn't? And Haskell is going to prevent you from doing such mistakes. And then in terms of the language design, this again relating to the paper, we show how to continue extending the type checker such that there's parametric polymorphism. You can add parametric polymorphism, traits, tracking linearity of variables, etc. Let me see that I think someone is trying to interact. Someone entered. Having said all of this, in this presentation, I'm going to show how to use a global environment, how to add backtraces, throw warnings, and statically prevent the use of untyped code when one expects it to be typed. The techniques that we're going to use are basically type classes, generalized algebraic data types, semigroup, monoids, functors, monad transformers, and finally data kinds for the last addition, which is type state. So prevent that you try to access some kind of untyped abstract syntax tree, but you expect it to be typed. Now the introduction. Let's see, what is really the type checker? So usually when you build a compiler, you define some really simple phases. You have some kind of source code, which is what I represent here at the left as the program. The program goes through the lexer and parser such that it produces some kind of abstract syntax tree. Then the abstract syntax tree goes through a type checker, which decorates the abstract syntax tree. I'm not assuming that we do any kind of transformation. I'm just saying that we take the abstract syntax tree that doesn't have any kind of type information, and we return an abstract syntax tree that now contains typing information. Usually you pass this kind of typed abstract syntax tree to the code generation, and it will produce, in this case, some kind of target code. Let that be transpiling from some kind of language to C, or transpiling in this case, or producing some kind of assembly code. We're going to focus on this thing. we assume that we already have an abstract syntax tree, and we're going to pass it through the type checker such that we produce an abstract syntax tree that has all the type information. Our language is super simple object-oriented language. It has classes with qualifiers for the fields, such that you can say whether something is mutable or immutable. The fields have types, and then we have methods. And the methods have parameters, some kind of return type, and then the body of the method, which is this kind of return E. We also have binary operators, so we must have numbers, basically. And expressions in this case can be, well, the normal things, right? Accessing a variable, using let bindings. We don't really have to use let bindings, but it's really nice because it allows you to put some kind of scope, so that's why we use them. You can do some kind of method calls, field access, binary operations, lambda calls, assignments, construction of objects, etc., etc. And the values that we have are the common true, false, some kind of numbers, functions, and null. Types are going to be just the classes that you define, function types, integer booleans, and the unit. Now, the type checker that we're going to design initially just throws one single error if the program is ill-typed. So if the types basically do not match. To do that, we defined a type class that we're going to call type checkable. And it has a type parameter that we write as AST so that it's easy to understand that you are supposed to place some kind of AST in there. The type check function takes an environment, some kind of abstract syntax tree, and is going to return the exception monad. This kind of except TC error AST means, is the exception monad? TC error, well, the TC abbreviation is always going to stand for type checking. So this is a type checking error, right? And the exception monad returns a type checking error or an AST. In this case, we're assuming that the abstract syntax tree is going to be the annotated abstract syntax tree. An environment in this case contains just a class table, which is a mapping from names to class definitions, and a variable table, which is a mapping from names to types, such that whenever you introduce a new variable, it has some kind of type. Now, if we were to take the abstract syntax tree, the simplest thing that we could do from the BNF syntax that I showed before is to start writing this in terms of algebraic data types. In this case, I'm going to go back for a second. An expression, we're going to show Boolean literals, so whether something is true or false, an assignment. So we say that an expression could be a Boolean literal, and it contains something called E-type. The E-type is the expression type. After the parsing phase, what we get is some kind of expression type that says that it's nothing. So in Haskell, we have the option type, which could be a just of something or nothing. After the parsing phase, this is going to be nothing because there's no type. We don't know what is the type. After the type checking phase, that is going to be some kind of just of some type, because the type checking phase, the only thing that it does is annotating, in this case, expressions and so on. It contains also a bval, which is the Boolean value, and it's some kind of Boolean. An assignment, for instance, has, again, some kind of E-type, which is the expression type. Again, after the parsing phase, the E-type is nothing. And then we have the left-hand side, which is going to be another kind of expression, and the right-hand side. Since we have a type class, we need to provide some kind of instance. So we declare the instance type checkable for the expression. And just to show how one can throw an error, we say, well, whenever you are type checking an expression, given some kind of environment, and that we're trying to do some kind of assignment, if we check that the left-hand side, so this kind of LHS and right HS is left-hand side and right-hand side. If the left-hand side is not an L value, then we use the common throw error from the standard library to throw an error. And the error that we throw is it's not an L value, and that's it. So are there any questions so far up until this point? Because this is the initial thing. If anyone wants to ask anything.
I think it's okay.
Okay, perfect. So now we're going to add backtraces. So currently, if we were to use this kind of approach where we just throw an error, what we could see without any kind of backtrace is that the error that we can show is error, there's no field Y in class X. We're kind of missing contextual information. A better approach to report an error would be to say, there's an error in the expression this.y, in the method foo, in the class X. But right now we have no access to all of this kind of contextual information. So we're going to fix that. To do that, we're going to add something called a backtrace. The backtrace has as the value constructor, so the thing on the right-hand side of the equals, a list of backtrace nodes. And a backtrace node is basically a class definition, or a method definition, or an expression, or anything like that. How do we see this? Well, when we're type checking a class definition, what we're going to do is to put the class definition as part of the backtrace. So now we know that we are inside some kind of class. Type checking a class definition means that we recursively go through and type check the fields and type check the methods. When we're type checking the methods, we basically do the same thing. We have the backtrace and we say, well, you know what? Add also this kind of contextual information so that I can say that I am inside this method. Type checking a method, what does it do? Well, it recursively traverses the abstract syntax tree, type checking expressions. So we go now to the expressions. Whenever we type check an expression, we go and add it again to the backtrace. If we find an error, then it's really simple. We just use this kind of backtrace, which we said it was a list. We use it as a stack. And when we throw an error, we can say, well, I just start popping. There was an error in the expression this.y. There was an error or in the method foo and in the class X. So this is how we can improve the design that we started with. Initially, we have this kind of type check function that takes an environment, and in this case, some kind of AST node. I'm showing the class definition for now. And after this, we know that we need to keep track of some kind of backtrace. Instead of putting the backtrace as a new argument to the type check function, because that is going to pollute the type check function, we can do something a bit better. We can just make the backtrace part of the environment, such that we don't need to pass it around. And we do this by just simply extending the environment that we had, which contained the class table, var table, some other things. Well, now it's going to contain something called BT, which stands for the backtrace. So we're not going to use this kind of thing that I said that is after. We're going to continue using the thing that says before, because I don't want to introduce a new argument when it's actually not needed. We need to see also how we're going to now push the elements into the backtrace. But before we do that, I want to say that before we were just throwing an error by using the common throw error function, which puts in the value constructor some kind of error, type checking error. And now we would need to replace anything that says throw error by a helper function that is called TC error. So again, it starts for type checking error that takes an environment and the error. And the only thing it does is going to call again the throw error function, except that now at the end, you can see that we extract from the environment the backtrace, such that the TC error has access now to the backtrace. So we can show nice errors. In terms of the implementation, we have the type class type checkable and the instance that we did for an expression in this case. The type check function is the one that contains the type checking implementation on how you do type check assignment. Now we're going to add a new function, which we're going to call do type check. And the do type check function is the one that is now going to contain the implementation of the type checking. So in a way, you can think of we add a new function and we need to rename what we had before as type check to now be do type check. And now the type check function, what it's going to do is given an environment and some kind of AST, it's going to call the do type check function, which is the one that actually performs the type checking. And we're going to update the environment. So we do this in this notation where we say the environment is being updated and I'm going to update the BT, so the backtrace. How do I do that? Well, now I go at the end and I say, I take from the environment the backtrace, and then I use the push function such that I push the new node to the backtrace. So this is what we said, right? We have the backtrace and we need to continue pushing items so that then we can pop them. Right now, this is the operation that pushes them, and I'm updating the environment. So after this, I think it's easy to see that the do type check function now works with the updated environment and then takes the abstract syntax tree and is going to return as before the exception monad. I
have a question.
Yes.
What about if language permit a deriving? So you are you can skip your type and compiler will derive that type during the compiler level. So you have here an assumption that the abstract this abstract model is already with the types, right?
Yes, yeah.
Okay, okay.
Yes,
okay.
yeah,
So,
yeah.
okay.
This is a super simple design for a common object-oriented language, like you could say of Java. So if you want to do a bit of type inference or something, then I think it's more involved because it's a different thing. I'm assuming that everything is annotated, basically.
Okay, okay, yeah. Thanks.
Yeah, no problem. And in implementation, before we were using the throw error function. Now we just need to replace it by the type checking error function. And that will be it. Now we're going to see how to remove a bit of boilerplate. This is something that I consider a good thing. Some people may prefer to not remove this kind of boilerplate, but maybe at the end you can tell me whether you think this is a bit nicer. So I have highlighted here the function called TC program. The TC program is the entry point to the type checker. And it says, given some kind of table and the abstract syntax tree of the program, I'm going to return either an error or the program. It starts by building the environment and then calls this function do type check, given some kind of environment and the program. I have highlighted that the environment is used there, and that we have also environments used in there, which is just passing things around. And it kind of makes sense. If you are type checking a program, you need to type check maybe functions that are in there, traits, classes. If you start type checking classes, well, then it means that now you take the environment, and because you are type checking a class, you need to add a new variable to it, which is this, such that it contains the current class name, right? So now you modify the environment, but overall you kind of always need to kind of keep track of this environment. And sometimes you want to do a modification. When you do a modification, this kind of modification is kind of a modification that runs inside a monadic computation because the type check function returns a monad. So in a way, we're kind of passing the environment around, but we don't actually have to. We could just go with some other design. Let's see. We have the exception monad, let's just forget about errors for now and focus just on having some kind of global environment such that we can use it in all our code. So in this new kind of design, we have the entry point to the type checker, which is the TC program. It contains the table and the program, and it's going to return just, we assume, an annotated program with all the type information. We know we have to build the environment, and then we have to fill out the blanks. In this case, there's something called the reader monad. That is what we want to use here, because it allows us to access an environment such that we don't need to pass the environment around. So it's something that lives in the monad, and through different combinators, you can modify the environment such that you can run computations in a modified environment. And then you don't need to pass the environment around. So the way to do this is just to say that now you need to run the reader over the type check function. How does it look now? Well, the do type check function takes now a program. There's no environment, as you see, at least initially. And the reader monad is the one that is going to contain the environment. Type checking a function, you see that we have this kind of map M for mapping some kind of monadic computation. We have the do type check function, and again, there is no environment that we need to pass around or keep track of. In case of type checking the class definition, we're going to use a combinator which is called local, which basically says, I'm going to modify the environment, and now you can run a monadic computation under this modified environment. So this just means that I modify the environment, and the map M computations that we have at the class definition are going to run in the modified environment that contains this name.
So yes, because so we have here this reader monad, but we are modifying this environment, or we are creating a new program based on that dependency that we provide.
No, we're modifying. Okay, so everything is immutable, right? So we're kind of mutating the environment such that now it contains something that is extended with this name and the class name that it contains, right? And then under this modified environment, you do the type checking of fields and methods.
Okay.
And after you're finished, the environment goes back to what it was. So if you don't use this added thing, then you're using the previous environment.
Okay.
So that's why we are not exactly modifying the environment. We're modifying the environment such that a computation can run in the modified environment. But after that, then it goes back to how it was before. Is it clear?
Yeah. Please continue, Fen.
But what about the errors, right? We had errors before, so what do we do now? Now, as I said, the design is a bit clearer because we don't need to keep track of the environment, but we need to still throw errors somehow. So do monads play well? I think they do. And for this, we know that we need to combine the reader monad and the accept monad. What we had before in the do type check function was to keep giving a program, I return a reader that contains an environment and the typed program. And now we want to basically, this is not Haskell notation, this is a way to say, well, given a program, I want to be able to access the combinators from the reader monad, and I want to be able to throw errors as well. How can I do that? Well, from the documentation, and now I'm just mapping, the documentation says that a reader contains some kind of R and A type variables. So I know that R is going to be the environment and A is going to be my program. The exception monad contains some kind of E and A. So E is going to be my type checking error, so the TC error, and A is going to be again the program. And now I see that there's something called a reader transformer. And let's see what does it do. It says that it takes an R. I know that R was the environment because I just did the mapping. I know that A was the program. So M must be some other kind of monad. And the other kind of monad in this case is just simply the exception monad that takes the type checking error. So this is all there is to monad transformers. I'm stacking one monad inside another one. I have the reader T, which is a monad, transformer in this case, but it's still like a monad. And I'm putting another monad inside, which is this kind of exception monad. I'm going to use an alias, which we declare in Haskell by doing this kind of type, that I'm going to call the type checking M for type checking monad that takes a type variable A. And what I'm going to say is that the type checking monad is basically this kind of reader transformer, such that I don't need to write all of that anytime I want to access the type checking monad. So now whenever I try to do the type checking operation, I know that it takes a program and it returns a type checking monad of a program. So that is not what we do anymore, right? It's the type checking monad. Now let's see how this plays with the type checking program. So when we were doing the type checking, before we used to do the run reader, now we call something that is the combinator named run reader T. And the run reader T basically takes a reader of blah, 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 so that kind of whole thing. And that is actually, if you look at the do type check function, that is actually what it returns, the type check M, which is the reader of blah, blah, blah. So, okay, so the run reader T takes that thing, and then it takes also an environment, and it's going to return an exception monad, okay? So I'm going to bind that kind of exception to the except, and then I just call, as before, the run except function, which runs the exception monad and returns either a type checking error or the program which should have been type annotated. We can do this kind of thing where it is clear that we're stacking or we're putting the exception monad inside the reader. But we can go for another approach which uses type classes, and I think it's a bit more clean. And I will not go through too much of the details, but the intuition in this case is that the type checking monad takes the type parameter A, and all of this for all M blah, blah, blah says, I'm going to return a monad of A that has access to the reader and to the exception or the monad error type class. So it's basically a simple way of saying, I don't know who is inside of whom, or I don't care. I just know that this kind of monad is going to have access to the monad reader and the monad error, and that's all. And this is going to play really well if you want to continue stacking more monads in the type checking monad, which we're going to do in a second. Was it a bit difficult so far?
Well, we are we are talking just right now, perhaps an abstraction way, a lot of abstraction here.
Yeah, absolutely. Okay. Now we're going to see how to add warnings. So far the type checker knows how to throw one simple error. So it doesn't throw multiple errors, just a single one. We have backtraces, and we use some kind of clean design with the reader monad. In the example that I show at the right, we have we bind X to some kind of object, and then inside the if expression, we bind X again to some other object. In some languages, this could be an error. In our language, we decided that this is going to be just a warning. So we're going to say, hey, you are rebinding, in this case, the variable X. So just so you know. And for this, we're going to throw a warning. Warnings in this case are not exactly like the exception monad. The exception monad as soon as it finds some kind of ill-type program, it exits in a way the type checking such that it doesn't continue monotonically accumulating exceptions. With warnings, we want to continuously accumulate warnings because we want to catch them all. So to define a warning, we create a new type constructor, which we call the type checking warning. And what it contains is basically just a warning and the backtrace. And again, the backtrace is the same as we saw before. It's something so that we know how to report nice warnings and errors. And a warning could be the snippet code that I've shown on the right is called a shadowing variable. So we're shadowing, in this case, the variable x. But you could also define something such as a variable is not used and so on. So different kind of warnings, basically. In this case, as I said, we cannot use the exception monad because it doesn't, as soon as it finds one error, it exits. So we need to kind of continuously or monotonically increase the warnings. And to do that, we're going to use something called the writer monad. So before, we used to have the monad reader and the monad error, so the reader and the exception, and the accept monad. Now, what do we do? Well, we just declare that the monad is going to have access to the combinators that are available for the monad writer. And we are going to say that there's a list of type checking warnings. And whenever I use a specific combinator from the monad writer, I'm going to basically say, hey, and put this kind of warning inside this list of type checking warnings. To do that, we declare a function that is called the TC warning, so the type checking warning. And what it does is, if you give me a warning, the asks function basically takes, I'm calling the BT, so the backtrace, takes the backtrace out of the environment. And then we bind basically this kind of backtrace. And we say with the tell function, hey, and go and put this kind of warning with this backtrace into the type checking monad. With this simple design, you just start basically adding things into the monad, and you don't care basically how things are added. So you don't need to explicitly say where it is, or you are inside the monad. It's kind of like the beauty of it. Now, the final thing that we're going to do is to use something called type state. This is going to blow your mind. And if you can understand just a tiny bit of it, I think that's really impressive, because it's really complex, but I think it makes a lot of sense. So we want to prevent compiler writers from using untyped abstract syntax tree when you expect them to be typed. So for instance, in the image that I show below, if we have an abstract syntax tree that doesn't have any kind of typing information, and you pass it through the type checker, I would expect that the tree that you return contains all the typing information. But right now, no one is enforcing you to do that. And we use type state to statically enforce that you actually decorate the whole abstract syntax tree. And if not, Haskell is going to complain about it, such that you remove those errors. So we want the tree to be fully decorated. Before we used to say that encoding an expression was using, let me see, I think there's someone either joining or this. Before we were saying that an expression can be simply encoded using algebraic data types. And we have bool literals that contains this kind of expression type. The expression type was using the maybe type, but this is kind of an ugly way of doing things. because it means that I always need to check whether something is nothing or not in order to know if there is actually, or in order to know if things have been typed. So we're not going to do this. We're going to use this kind of notation instead. And I'm going to explain what it is. So expressions now have a type parameter, which is this kind of P. And each type parameter is going to be of a kind, which is phase. So we want to say, if something came from the parsed phase, then we know that it is not typed annotated. But if something goes through the type checking phase, then it must be annotated, because if not, then I don't know what's going on, but that's not the right thing to do. And this kind of phase kind has a functor, which we call as F. Now, phases, as I said, is the parsed phase and checked. Now, this kind of phase is a generalized algebraic data type. And we declared F to be the common functor. So I think this is typical for system F omega. So it takes a star and it returns a star. Fine. If you are the parsed phase, then you're going to use the proxy functor. And if you are in the checked phase, then you need to use something called the identity functor. The proxy functor has A as a phantom type and it just ignores it. And the identity functor is just the identity. It's that the functor that is the identity. So the important thing to notice, all of this is a bit abstract. When we go through the example, I think it will be much more clear. The important thing to notice is that different phases carry different functors. Let me see, there's someone trying to do something. Chat. A phantom type parameter is one that is not used. So it's something that you declare in the proxy of A, but then you don't use A for nothing. So it's just phantom. You don't do anything with it. It's not on the right-hand side. It's not used on the right-hand side of the proxy in this case. Good. Let's see. So as I was saying, when we go through the example, maybe it's a bit more clear, because so far it kind of is a bit fuzzy. And by the way, for the phase, phase right now is like a type. We use an extension, which is the data kind. And I think there was another one that I forgot, such that the phase is now a kind, not a type, because otherwise this would be a type, and it's really not a type, it's a kind. So the two type check function now takes an AST, and we use this kind of single quote to say that we are in the parsed kind, or it is of the parsed kind. Whenever you start doing the type checking, you must get something that is parsed. So it hasn't gone through the type checker yet. And it's going to return the type checking monad as usual with an AST that must be checked. So let's see, if we go with a Boolean literal, we need to say that type checking a Boolean literal is basically returning basically again a new Boolean literal. So just the first part that I have highlighted over there. And if we map to a Boolean literal, we see, okay, a Boolean literal takes as the first argument something which is the expression type, and there is some kind of F. Okay, where does the F come from? Okay, so the F comes from that kind of phase. And we know we want to get something that is checked. So let's go and see the checked phase. The checked phase says that we need to use the identity functor. And the identity functor, what does it have? Well, as a value constructor, it says that it has the identity and then some kind of name thing, right? So I just go and put the identity, and that's it. So overall, if you want to make sure that something is checked, you need to wrap it around the identity functor. And if not, Haskell is going to say that whatever you are doing is not right because it has not been checked. This is a way to basically also sidestep the problem where you have some kind of abstract syntax tree, which maybe only works for parsed thing, and you define exactly the same abstract syntax tree in which you require things to be completely typed. So instead of creating 2 abstract syntax trees, you reuse the same one, but you rely on kinds in order to say whether something has been parsed or checked. Let's go through another example. There's a function called getType. And if you try to get a type of some kind of expression, it must be because it has been checked. If it's not checked, then you wouldn't get any kind of type. So before we would have done, given some kind of expression, I return a maybe of a type. And then now you need to check whether something is nothing or whether it actually contains some kind of type. Now, statically, Haskell knows that if I pass some kind of expression that is checked, then the type must be also well-formed, so it must be checked. Let's again go through the example. So we have some expression that it says that is checked. Because it's checked, I know that I just go to the faces, and I know that the functor that this uses is the identity. If we go through the and look at the identity functor, we know that it contains something called the run identity. Okay, so from the expression, I extract the expression type. And if we could look at the top in the declaration of the expression, we know that all of them has this kind of expression type where there is an F and then the type, right? So I know that the F is going to be the identity. So I just want to extract the type out of the functor. So I call the run identity such that I extract the type, and that's it. And it must be checked because in the declaration of the expressions, this kind of type parameter P says that if one is checked, then all the other P's must be exactly the same, so they cannot be different. So I know that if I try to get the type out of a checked expression, then I'm going to get a checked type, so a type that is also well-formed. As I said, I think it's difficult to understand, but I think that the trick is really, really nice trick, such that you know that statically, Haskell is going to reject programs in which you forgot to type check things, because you need to wrap them. In this case, if you want something to be checked, you need to wrap them through the identity functor. And if not, then Haskell knows that whatever you're returning is not going to be right. So the Haskell type system prevents statically compiler writers to use untyped code when one expects them to be typed. Now, referring to the paper, there are more goodies and good explanations in written form, because in a presentation, I think this is a bit too fast and too heavy. There's also comparison against PureScript, Haskell, Elm, and a bit about Scala. So if someone is into Scala, then you can see as well how we make some, we differentiate from them. In summary, basically, I've shown heavy probably description on how to create a type checker. The type checker design uses the reader monad, monoid, functors, applicatives, etc., etc. We also have an artifact, which I think is in the meetup notes in case someone wants to check it. And with this, I think I'm finished with the presentation. Thank you.
Thank you very much. Thank you very much, Kiko.
Yeah, thank you. Thank you.
Does anyone else have any questions? Let's see, where's the chat here? Clap, yeah. Do anyone have any questions? Or?
I really think it was a bit heavy, but I think
yes, not super simple.
But I think if you try to understand it and maybe look at the video or read the paper, then after a few times you will get it, and especially the last part, yeah. I thought it was mind-blowing. So yeah.
The last part was whoa, super hard to understand. Well, I lost somehow. Yeah. I will have a look about. So this Phantom parameter type, for what reason we define it, as it's not used on the right side on the equation. So we have this.
Right. So if you want somehow to say that something, this is now maybe not really regarding the type checker, but if you want to enforce that something you want it to be considered as an int or something, then I think you use some kind of phantom type to fix basically what you consider it to be. But to be honest, I've been like more than 6 months without doing Haskell, so you lose quite a lot when you don't do it daily. Okay. So yeah.
Okay.
Thanks. Anyone else has any questions or?
Yes. I have a question. I wondered about the use of the backtrace.
Yeah.
And I wonder if you, I mean, it kind of made me think about like using a kind of a zipper data structure, and would that have worked as well, or might even actually be nicer because you have the
which kind
both
of
sides.
Data structure did you say?
So you have the backtrace where you just keep a list of all the parents of the current level of the AST, which is in a way what you do in a zipper when you define a zipper for actually for all recursive types.
Okay, I don't know if I understand correctly, but what is a zipper?
Zipper.
Can you write it in the chat?
Yeah.
A zipper, all right, but a zipper isn't a function that takes two things and put them together?
No, it's a kind of a data structure that encapsulates traversal over some other data structure. So, for example, a zipper for a list would be a list of it will be a triple of like the current element, or actually it can be just a pair. It can be like all the elements that you've already visited.
Yep.
And all the elements that you are going to visit, starting from the current one.
Yeah.
And the nice thing with the zipper is that it's very easy to reconstruct the data structure from the zipper. So it kind of lets you to traverse the data structure, but you can also reconstruct it.
It seems like it could be a good fit. I was not familiar with this zipper data structure, so that's why we didn't even think about it, I think.
Okay.
But I will take a look because it could be actually an interesting change. So why not? Yeah. Thank you.
Yeah.
Yeah. Do we have any more questions or? Otherwise, as soon as, we'll put out the recording on YouTube. I think you have put all the sources you sent over, Kiko, and put them out on the meetup, and we'll put them up on YouTube also below in the comments or whatever it is, so everyone can read them again.
Sure.
Yeah. So thanks for a nice presentation, Kiko.
Yeah. Thank you everyone for listening.
And thanks everyone for joining.
Thank you.
And
Thank
continue to have a nice and nice evening or afternoon.
Yeah, thank you.
Yeah.
Bye.
Thank you very much.
Bye bye everyone.
Bye.
Bye.
Bye.